Hey guys! So, today's video is going to be a continuation of the PowerPoint we didn't finish in class. So the first few slides will look very familiar, but then the rest is new content. So treat the first few slides like a warm-up, and then we'll get into the new stuff. Alright, so as a reminder, we are talking about simplifying radical expressions, which means we are dealing with expressions that look like this. Okay, so the square root function. Now, as a reminder, when we are doing this, we are looking for perfect squares. Okay, so perfect squares, these are your 4, 9, 16, 25. Okay, all of those, there's more of them, but those are the first 4 that I can think of. You've also got 0 and 1 in there. Sorry, my iPad. Okay, here we go. Now it's fixed. So you also got 0 and 1 in here somewhere. All of these are perfect squares, which means their square roots are going to be 0, 1, 2, 3. Okay, you know all these. So you're looking for either perfect squares or you're looking for pairs. All right, more specifically, factor pairs. Okay? So that's the thing to keep in mind when you are dealing with square roots. So this slide will look familiar. We did this in class. For this first problem, 5 and 10 are not perfect squares, nor are they pairs, but 10 has a 5 times 2 inside. So I'm going to simplify this. I'm going to combine like terms because they're both under the radical, and I'm going to say the square root of 50. Okay, so they are both radical terms. They are both underneath the denominator, are both underneath the radical. So when I multiply them together, they combine. And now I can actually simplify the square root of 50 in a different way. So I can say this is the square root of 25 times the square root of 2. Okay, well I know the square root of 25 is 5. The square root of 2, it doesn't simplify nicely, so it's just going to come down, and so my answer is 5 root 2. Okay, so that's one way. You can either combine your radicands and then break up that number into one of perfect squares, or, like in 2b, if I combine these, I can put them together and get the square root of 48. But right off the top of my head, I don't know what perfect square goes into 48. Maybe you do. If you do, congratulations. I'm going to assume we don't. So what you can do is you can actually break up these radicands further and look for either the pairs or the perfect squares. Here we go. So 6 will break up into the square root of 3, and it'll also break up into the square root of 2. Square root of 3 times the square root of 2. Okay, times 8 breaks up into the square root of 2 and the square root of 4. All right, so now I'm going to go through my options. Square root of 3, it's stuck. It doesn't do anything. It's neither a perfect square, nor do I have a pair. I do have a pair of 2's right here, so this will simplify to just 2. Okay, I have a pair, so one of them is going to come out at 2. And then my square root of 4 over here is also 2. Bring down square root 3. Okay, now notice square root 3 is the only number inside the radical. So that's going to stay inside the radical. I'm going to combine my two like terms, and my final answer is 4 root 3. Okay, it says 2 times 2 is 4, and then the square root gets tagged along in the back. Okay, so these are the two different options you have. The first one, combine them and look for the perfect square. The second one is keep breaking them apart and look for your pairs or your perfect squares that are within the number. All right, let's do some new problems. Now remember, this whole concept of square and perfect pair applies to everything underneath the radical, even your variables. Okay? So what I'm going to do with this one is I have 32. I'm going to bring it off to the side. And the square root of 32 will break down into, I'm thinking of square root of 8 times the square root of 4. Okay, well that's great. I already know what the square root of 4 is. 8 is going to have the square root of 4 times the square root of 2. Okay, and actually, there's a pattern right there. I have a pair. I have 2 square root 4s. Okay, so that means one of them is going to come out, and I've got a 4 root 2. If your brain immediately went to 16 times 2, very good job. If your brain did not, this is how you do it. You break it up into its pieces and look for either pairs or perfect squares. Okay? Now, next, however, I'm going to do my variables. So I have r squared, which is r times r. I have k to the 4th, which is k times k times k times k. And then I have t to the 5th, which is t times t times t times t times t. Okay? Now, I know I've said it a million times, but we are looking for either pairs or perfect squares. So for my r's, I do have a pair. I have a pair of r's here. So one of them is going to come out of the radical, and the other one goes away. So as I rewrite my problem, I've got 4r at the very least. Okay, here's my answer down here. So now I'm going to do my k's. In my k's, I have 1 pair, and I have 2 pairs. So one is going to come out from this one, the other goes away. One is going to come out from that one goes away. And I end up having 2 k's left over, which is going to be k squared. Okay, because I have 2 k's that came out. All right. Next, I have 5 t's. I'm going to do the exact same thing. Here's a pair, and 1 is left over. So now I'm going to do the same thing I did with the k's. I'm going to bring one out, throw the other one away, bring one out, the other one goes away, and I'm left with t squared on the outside. But this t did not have a buddy, nor is it a perfect square, so it goes inside the radical with the leftover number. Okay? All right. Do the next one. When the video plays again, you'll see the answer. And there's your answer. Now with this one, as you can see my work off to the side, I started with my number, and I broke 56, or the square root of 56, up into its factors. Now this time around, I did a factor tree. I think a lot of us are maybe more familiar with the factor tree, but just so that you can see both strategies. And I found that there is there's a 4. Square root of 4 is 2. But then there's this other 2 and this other 7 that are stuck inside. And that's how you get the square root 17, or square root 14 on the inside. Now, when I break down my variables, you may be starting to see a pattern by now. All right? And the pattern is that when it's even, dividing your exponent by 2 will tell you what comes out of the radical. Okay? So in this case, I have x to the 1 power. Well, that's not even, so that x is going to stay inside the radical. Then I have y to the 10th. Now I broke it up in y to the 4th, y to the 4th, and y squared because we had these examples over here with k to the 4th and t to the 5th beforehand. And so in k to the 4th, what came out was a k squared. And so I took y to the 4th and brought out a y squared. Took the square root of y 4th again, got another y squared. And then the square root of y squared is y. Since all 3 of those things are out of the radical, I can combine them freely. And that is where y to the 5th came from. Or that is where y to the 5th came from. Then finally, z to the 5th. We did the same thing earlier with t to the 5th. Again, I broke it up into z to the 4th power. 4 divided by 2 is 2. So a z squared comes out. But then this leftover z stays inside of the radical. Okay? So whenever you have a positive radical, or positive exponent, you can just divide the exponent by 2, and that is the correct exponent that comes out. If the exponent is odd, you can still divide by 2, but whatever's left over is going to stay inside. All right, let's move on. Now, earlier in your notes, you should have written down that you cannot have a fraction under the radical. It's one of our rules. However, when you have a fraction under the radical, what you can do instead is take the square root of the numerator and the square root of the denominator. Okay? Once you've got that figured out, you still have to simplify as far as it'll go, but you simplify them individually now. So you simplify the numerator as far as it'll go, and you simplify the denominator as far as it'll go. And I have 4 examples here. Now, the first thing we're going to do on all of these is we're going to rewrite them. Okay, square root of the numerator, square root of the denominator. Once we do that, we can simplify. So this first one, you can rewrite it as the square root of 1 over the square root of 4. Okay, so the next question is can it simplify? The answer is yes. The numerator simplifies to 1, and then the denominator simplifies to 2. That's your answer. Let's go to B. With B, I can break this apart. I can do the square root of 3 over the square root of 25. Now, square root of 3 does not simplify nicely, so I'm going to leave that alone. And now I have the square root of 3 over 5. Okay? You guys do the other two. When the video plays, you'll see the answers. All right, here are your answers. Now, what I want to draw your attention to before we move on is on letter D. Notice how I didn't simplify my fraction before I rewrote it. See that? The reason why I did this is because I noticed my denominator was a perfect square, and that when I rewrote it, it would simplify completely and very nicely. Okay, so I left it alone for the sole purpose of when I rewrite it, it would factor out. If I tried to simplify it beforehand, I would have been left with 4 over 5 square roots. And while that would have been nice for the numerator, it is not so nice for my denominator. And if you remember from the previous couple slides, one of the things you can't have is you can't have a radical in the denominator. So if ever this does happen, we've got to get the radical out of the denominator. All right, now that's the next slide. Before we leave, again, I want to remind you, sometimes it makes the best sense to leave it alone. That way you can take the square root of the perfect square. So with this one, all right, now we need to talk about rationalizing the denominator. Rationalizing the denominator is a fancy phrase you really need to write down because it is how we eliminate radicals in the denominator. Okay, this is how we do it. And the way we do it is by multiplying. So we are trying to get the radical out of the denominator, so keep an eye on the denominator. In this problem, I have the square root of 12 in my denominator. So what I'm going to do is I'm going to multiply the top and the bottom by the square root of 12. Any square root multiplied by itself is just that inside number. So 12 is left and the radical goes away. Now in my numerator, 6 times 12, I could do that, or I could leave them apart. All right, I know I have 6 times 12 can be broken up into 6, or to 6 times 2, and then I have that leftover y. Reason why I did it like this, or maybe you can tell already, is because now I have a pair of 6's. So one is going to come out, the other goes away. And I am left with 6, the number that came out, the square root of 2y, which are still inside, all over 12. All right, here is the last trick. When you are dealing with radicals, you can only combine like terms. Okay, so a radical, it doesn't matter what's inside. If I have square root of 3, if I were to try to multiply that by 5, it would be 5 square root 3. Okay, because 5 is not under the radical. Therefore, they don't combine, they just kind of hang out next to each other. All right, same thing with division. If I have the square root of 2 over 6, okay, this is my final answer. I can't simplify further because 2 is protected under the radical and 6 is a regular number. Okay, so you cannot combine regular numbers with radicals, or radicands to be specific. Back to our problem. I can't touch 2y, it's in the radicand, or it's under the radical. I do have 6 though, and I have 12. Those numbers I can simplify. All right, so 6 divided by 12, this is going to be a 1. This is going to be a 2 down here. My final answer is 2y, square root of 2y over 2. Okay, again, I can't combine those terms any further because the 2y is underneath the radical and I can't touch it. All right, now, in the last problem, that was just with one number in the denominator, or one radical. But what happens if you have a binomial? I knew you were wondering. So in this problem, before you get too mixed up, in this problem we are starting here. Here's our problem. We have 3 over 5 plus root 2. Our problem is that we have 2 terms in the denominator, so it's not just a simple fact of multiplying. I have to multiply by something called the conjugate. Now, the conjugate is when you have the same numbers but opposite signs. Okay, and if anybody remembers the difference of 2 squares, if I have a plus b times a minus b, what's going to happen is when I multiply, I'll have a squared, then I'll have negative ab, I'll have a positive ab, and then I'll have a negative b squared. Okay? My middle term is going to cancel out entirely, and I'm just going to be left with my first term and my last term. This is what we're doing here. If I take 5 plus radical 2, and I multiply it by 5 minus radical 2, when I distribute, I'm going to have 5 times 5, which is 25. 5 times negative 2, which is exactly that, 5 times negative root 2, plus 5 root 2, and then the square root of 2 times the square root of 2 is negative 2, because a radical multiplied by itself is just that inside number. The reason why we have the conjugate, the reason why we change the signs is for this step right here. My 2 remaining radical terms are going to cancel out. And now I'm going to be left with 25 minus 2, which is 23. All right, and as you can see here at the end, that ends up being our denominator. Okay? Now, in the numerator, as you can see in this step, what you're going to do is you're going to multiply the conjugate to the bottom and the top, the numerator and the denominator. I just walked you through what happens in the denominator. But what happens in the numerator is you are going to distribute into the conjugate. Okay? Now, if you have a binomial times a binomial, you're going to FOIL, just like we did in the denominator. But in this case, we have a monomial times a binomial. So when we distribute our 3, we end up getting 15 minus 3 root 2. And since we can't combine our numerator any further than that, here's our final answer. Okay? Now I know that was a lot to process, so here's a problem. What I want you to do is I want you to look at the example that you wrote in your notes, and I want you to try to solve this problem first. The video is going to pause. Try to solve the problem. When it plays again, we'll go back over it. All right, let's go. So I look at this problem and I immediately see that I have a binomial in the denominator. So I'm going to need to multiply the top and the bottom by the conjugate. So that's going to be 3 plus root 7 divided by 3 plus root 7. Now remember, the whole point of doing the conjugate is to cancel out that middle term. So all I need to do for my denominator is follow that pattern. So here we go. The pattern is I'm going to multiply my first term by my first term, which is 9, and then my radical term times my radical term, which is minus 7. I don't need that middle term because if I did FOIL, that middle term would cancel out. In my numerator, I have 7 times 3 plus the square root of 7. Okay, let's keep going. In my numerator, I'm going to distribute, which means I have 21 plus 7 times the square root of 7, all divided by 2. Now, there's nothing I can do to simplify this further. I can't divide anything out, so this is my final answer. And that is all I had for you today. Good job. Please write down any questions you have, and I will see you next time.